adding the material and completing the product. Actually, this is a puzzle, one piece of this puzzle. Maybe if you want, you can solve it. Presentation. Somehow connected to that. Actually, it's the language. It takes time first to print something. When you are printing something more complex, usually you have to use some supports which are removed after the process of printing. Or maybe you can solve this with different position of the object at the beginning. It's also possible. Or you can divide the object into more pieces which are printed and then after the printing connected, glued together. For example, a sphere. Without support, the sphere, the program, so inside the sphere into pieces, and then it's glued together. And supports. Actually, I thought the video it's faster than in real, so I think that one piece, maybe one other. But you can see how it works. Then you can see the final product. Okay, so this is how it works, and now how to prepare step the digital model for printing. So sometimes we want to get exact replica of something that already exists. This is quite common in industry that some part, for example, of engine or I don't know what exactly needs to be replicated. So you can use 3D scanning. This is an example of compact 3D scanners. Actually, these are my hands because I was dealing with this a lot during my PhD studies. And for example, I was scanning special surfaces, facial surface, and I was dealing with new algorithms for computing polygonal mesh, which represents the surface of the object. So this is one possibility. Optical 3D scanners, actually, this is based on photogrammetry. It's the object is photographed from more perspectives, and then you can get 3D coordinates of points. And I forgot to say that the output of 3D scanning is only an unorganized finite set of points. It's called point cloud in the three-dimensional space. Nothing more, actually. So only point cloud. It's only points in the three dimensions. It's the coordinates. You cannot print it, of course. So further processing is needed. You, for example, have to compute the polygonal mesh, which represents the surface of original object. So compact scanners, optical scanners, or laser 3D scanners. Here you can see the process. So at the beginning, we can get point cloud, and then we need to compute polygonal mesh. Usually triangle mesh. Nowadays, it's very modern to work with quadrilateral meshes. Both has some advantages and disadvantages. It's easier to count triangle mesh. But actually, many scanners, or maybe all of them, nowadays have some integrated software which count the polygonal mesh. Even you can smooth it, and you can do some mesh simplification within that software. Then you can do some further modification in some CAD softwares, for example. And even it's possible to count, to express reconstructed surface in a compact description, for example, with an analytic surface. But this cannot be done in general, of course. For example, when I would like to scan my hand, it cannot be described with one parametric equation, for example. It's not possible. There can always be some simplification. I will do that. But polygonal mesh is enough for 3D printing. So I can have polygonal mesh, some approximation of the surface which can be printed. If I have some good accuracy, it can be almost as the product that I was scanning. So here you can see the whole process in the images. So we can get from scanning point cloud. I'm not sure if you can see it, but this is polygonal mesh, triangle mesh, which approximates the point cloud. Actually, this was done using my algorithm. I was developing algorithms for surfaces of revolution. So this is my own algorithm. Actually, it made less mistakes than the professional commercial software because it wasn't modified for rotational surfaces. Of course, I was working with that property that is a rotational surface. That's why I got better meshes than the commercial software. Okay, so this was how to scan some real objects. Also, maybe I was hiding some another facts. It can be, maybe you think now that it's very easy to scan something and to get the polygonal mesh. But again, if I want to scan my hand, it cannot be done just from one perspective. I cannot see it I cannot see the whole hand. So sometimes I need to make more scans, and then I have to fit all scans together. So this can be also quite difficult problem. And again, there are some methods how to do that, but it can be quite difficult to do with this. So another way how to prepare digital model is to directly model in some 3D computer software. The easiest way how to do it is to use some free software, for example, GeoGebra. You probably know GeoGebra dynamic software, which offers we can directly export digital model into STL format, which is the format in which you can save digital models and then print them. So maybe I can show you some simple example. I can model a few. Okay. If it won't work. Yes, okay. And then I can what I will model here, I can directly export it into STL format. So if I want to see it, here you can see that it supports STL formats, which are necessary for 3D printing. So maybe I will do it. Oh, I forgot one thing. It will print everything what I have on the screen. Actually, also the axis and also the gray lines over here. I can involve some more options here. Maybe the scale, the thickness. It's the thickness of the line. So I will okay, we will see. Okay, I have to find my folder. I try to do this. One thing, write STL. Yes. Okay, so we have cube for 3D printing. Now we will see what I have to do there afterwards. I will do it later. So I will go back to my presentation. What is again the disadvantage of this software? There are no advanced features for modeling. for example, constructive solid geometry that is normal in professional CAD software, for example. It cannot be used in GeoGebra, but you can describe surfaces with parametric equations, so this can be done in GeoGebra. So, for example, pupils and students in secondary school, it can be really good tool for modeling. So what I'm using.
But you need a solid,
Sorry, sure. I will show what I have to do with the model when it's only a surface. Of course, it doesn't have any thickness, so I can print it. So what I'm using for modeling, I'm not sure if you know, Rhinoceros software. We can use some CAD software. I'm not so friendly with them, so I'm using this one, which is a commercial NURBS-based modeling, 3D modeling tool. It's commonly used in the process of design. So production industries are commonly using this software. And it has a wide range of various types of digital geometry, such as solids and NURBS. And also, it works with constructive solid geometry, as you can see here. So with some simple primitives, I can, using Boolean operation, I can model the final object. So here I use union and division, and I got the final object. Another way how to use this software, we can use a combination of a set of surfaces to describe a single closed volume, as we were asking. So there are traditional techniques how to generate surfaces. For example, to extrude a curve, to screw a curve, to revolve a curve, to sweep a curve along a rail, and some others, which is quite common in computer graphics usually. They are describing surfaces in this way. So here an example, a parabola is sweeping along another parabola which is oppositely oriented, and we can get in this way a hyperbolic paraboloid. And as you said, it's a surface which doesn't have thickness, so it's just an abstract thing in mathematics, so it cannot be printed. So what I'm using, I'm trying to use this surface as a part of some solid, as part of the surface of some solid. So this is a part of that hyperbolic paraboloid. Then I use two parallel planes and another perpendicular plane. And I cut it, the surface, and I actually printed a solid figure, which has hyperbolic paraboloid as a surface, as a part of the surface. So this is why how to do that. Or Professor Vejcik has sent me some model of a surface. Another way how to do it, you could use offset, some offset of the surface, and actually print this surface with some thickness. But the offset is not already the original surface. And it can be, of course, problematic when the surface is somehow more complex. And for example, intersects, it's intersecting by itself. So this is the process of producing the final model, and the final model is here. Or here another example. The surface of revolution. This is rotational hyperboloid. We have two screw lines. One is rotating along the other one. And if you use some transformation, again in that software, this is some affine transformation, you can get non-rotational hyperboloid. Another way how to do it is to describe surfaces in parametric forms. For example, and here you can see root surface. It's called Kipper-conoid. And I used only part of it. It's a root surface, so you can see two lines which are on the surface. They are intersecting one line, which is z-axis circle, and it's parallel to some plane. You can see the equation and the final product, which I have also here. And this is another conoid. Again, a root surface intersecting intersecting a line, a circle, and again, it's parallel to some plane. And I also do here. Again, just a part of it, it's continuous, the infinity, considering lines, not segment lines on the surface. And if I'm too lazy to model something by myself, I can use some websites. There are 3D printing communities with millions of free downloadable 3D models. For example, Thingiverse. It's a famous website. But actually, I don't like it too much because usually I want to get the model of some properties that I want to do to myself. So I usually use my own models. So now we have digital model. We do it using any of these methods, 3D scanning. We directly model it in 3D software, and we get digital model in STL format, as I did in GeoGebra.cube. So STL format, just to be clear, it's an unstructured triangulated surface by the unit of normal and vertices of the triangles, and it's using a three-dimensional coordinate system. But now I have to convert this format into G-code format, which is quite common. It's computer numerical control programming language because we need to describe how the tool is moving in three dimensions. So how the nozzle from which the melting material is coming out, how it is moving in space. So it's coded in G-code format. So it describes the path of the tool. And there are actually many software, many control interfaces, free control interfaces, which enables to do this. So I can show it to we have that here. And this is one software which will convert STL format to G-code. So I will open the so here you can see the digital model. We can do some modifications that we can change the scale, we can change the position much more. So I will slice it now. So it means that you can see it, the individual layers. If I zoom it, so you can see layers, how it will be printing. So layer by layer. And of course, it's working with some accuracy. So this is very simple, of course. You can make the cube from another material. You don't have to print it, but just for an illustration, I wanted to show you. I will show you some another example. Let's try to slice something more interesting. This is a helical surface, which is defined by skewing a circle in a horizontal plane. And maybe here you can see if I slice it. So this is still 5D, doesn't need any support. Maybe I can change it, and I will want some support that you can see how it will look like. So look at this. It can happen that the model will need some supports, otherwise it cannot be printed, so you have to remove this afterwards. Okay. it can be quite difficult. So then it's not smooth, and you have to somehow modify the final product. So it's better to avoid this. Okay. So now we are ready to print it. Sorry that I again didn't bring the 3D printer. So here you can see again the control interface and also another one on the left. So now we are able to print the model. So what can we do with printed models? So as I said, I'm using them in education and at secondary school mathematics within the topic of solid geometry, of course. And I can show the properties of and relationships between geometrical objects, and students by themselves, they can use the final products as visual aids. A very typical example of what we are doing with students at secondary school is to determine the relative positions of, for example, two lines. If they are parallel, intersecting as two, and imagine this task only with the projections. You projected it, not to use any visual aid, but they are solving these tasks only in the projected situations in the plane. When it is depicted in the cube, it can be easier to imagine how it looks like in 3 dimensions. But if I take the model into my hands, I can immediately see the position of two lines. So it really helps. Or you can not only use physical models, but also digital models. For example, again in GeoGebra, which is students are very familiar with using, for example, GeoGebra or other modeling software. Actually, I'm comparing what is better in my didactic research, and always students are better when they have at least some visual aids when they are solving. So this is one way how to use it. I don't know how it works outside the Czech Republic, but in the Czech Republic, there are actually some education programs which support using, for example, 3D printing at schools. So I use this opportunity, and together with my students at secondary school, we proposed such a project. It was called Training of Spatial Abilities, and it was about tessellation and solid figures. And the company who is producing 3D printers, they like it, and actually they offer 3D printer to our school for free. So first we proposed the project, then they offered the 3D printer. We printed everything, we fenced our project, and then they decided that the 3D printer also gave to us to our school. So it's about tessellations. For example, we prepared the construction set of polygons. I'm pretty sure that you know this. So it's a set of regular and irregular polygons, and it's based on principles of tessellation. So students were actually helping me with the printing. They were modeling the polygons, which was extremely easy, but they were actually joining every stage of the process, and actually they learned a lot about polygons, about the properties of planar geometry, and they were enjoying that they can model, they can print, and they can use this modern technology. So I also wrote this and tried. First task was that I was giving to them was to find tessellation, regular tessellation. Usually they were able to solve polygons with large triangles. But then when we are combining two sides and small sides, it was more difficult for them. But when they were using set of modules printed on 3D printer, it was easy for them to find all tessellations. And another part of the project was that we were printing wireframe models of solid fibers, as I showed you. So not only wireframe model of steel, but also pyramids. Actually, this was quite difficult to figure out how steep it could be that it can be printed in one piece. And another thing that I'm proud of is to look at that. It can be put together that it's touching the bottom of the piece. So this was the project. And I'm not only a secondary school teacher, actually I'm mainly university teacher. So I'm using these models also in descriptive and differential geometry courses. Maybe you can say that it's too simple to use this at school, at university. But when we are describing surfaces with parametric equations, we are, for example, computing tangent lines and I will in differential geometry. So, for example, such models, and I'm showing my students that this is created by doing a line, and I can show them this abstract mathematics in real. They can understand much better because always visual aids can really help. For example, the tangent plane here can be determined with lines which are on the surface. So I think it's easier when they can see it in comparison with just computation on the blackboard. So here you can see another examples of root surfaces. Of course, again, just a part of the surface, and it's a solid surface. So here you can see another gallery of models for secondary school mathematics, or here another models for differential geometry courses at university. So what I would like to show you lastly is also work of my students from university. This was super good student. She was dealing in her master thesis with applications of surfaces in mechanical engineering, and she decided to deal with mathematical and geometric description of surfaces. And she focused on spheres, tools, gears, and other machine parts. And she was describing the geometry, what is behind, and it's really beautiful. So here you can see some threads which are helical surfaces, of course. Here you can see self-centering three-jaws place, chuck for clamping rotating parts. And she describes everything in mathematical way. So you can see, for example, that it's Archimedes scale. So again, nice geometry. And all these models she modeled in computer modeling software, and she printed. And it's really working. It's a functional model, so you can really have something inside here, and it can be printed. And it's really part of some real machine which is using in the production industry. And students can learn that geometry, what we are studying at school, at university, it's not just theoretical field, it's really used in practice. This is always my way I need to show students that it's not just theoretical mathematics. This is one thing. Another model, this is ball track. Again, beautiful geometry, what is behind. For example, Archimedes serpentine, which is created as an envelope of moving spheres. Of course, it's in bigger scale. another ground drill bit, which is created by machining, that we are removing some material to get this ground again. And finally, some applications in outside education, and what I found when I was studying 3D printing. So maybe this you can know that this was a big project that some people were creating a replica of Michelangelo's David marble sculpture, and it was placed at Expo in Dubai. I think last year, or it was somehow postponed. I think it wasn't in 2000. It wasn't at 2020, but it was postponed. I think last year. So if you're interested, you can show the video. You can see the video of how they were painting. First, the scanning, where they used this 3D scanning technology to get the digital model. They were scanning the real statue, which is a good method. If you cannot destroy the original statue, you can save the replica for future generations. And of course, this was very difficult to do because they had to do many scans, then fit together and find the final polygonal mesh. I was showing just the final product. And it was in COVID pandemic. Here you can see also see some holes because it wasn't finished. So here only the digital model. And then they were printing it, of course, on a larger printers. And some time. I think that statue has 6 meters something. And then they were transferring the people by. So, very interesting project. What else? You can use 3D printing just for decoration, for some fine arts. And here are some more examples. In the arts, in the furniture designing, fine arts, jewelry. Well, actually, I'm also making jewelry, so these are my own designs. These ones. Also in medicine, for example, to create some individual braces which can be printed for individuals. So according to the size of concrete people, or of course in some automotive industry, or maybe you saw a printed houses, and it's almost everywhere. So for the future work, I would like to extend my array of models, and what I already said, I'm still comparing what is better in education. Some are doing some research studies and comparing what helps students when they are learning geometry. And at every level, at university, at secondary school, it doesn't matter. It can be at every age. Okay, so thank you very much for your attention, and I'm waiting. So, are there any questions?
So have you ever used anything other than the plastic to?
Actually not. That 3D printer what I'm using, it's able to use another materials, but I'm using only some basic it's plastic. Actually, they are even saying that it's biologically degradable. So,